when you record, it appears in the Teams chat. But one thing I don't like about Teams is it records the whole screen and the participants, which is kind of a pain. It uses up half the screen just to have these little icons sitting there. This, I get the whole screen. I think it's a little better to read. And why doesn't it record? Any questions about any of the algebra functions? Anything stuck on that? I'm happy to review any of that. Otherwise, I'm going to go on to inverse functions. Yes?
Maybe
the graphing part. Like, okay, let's jump to the graphing part. Let's go bring up an example there. And that was, where did it go here? Gotta find it now. Let's see here. Well, I guess I'll just pull it down off of Moodle here. We'll do a little review of using graphs to find when you're doing algebra functions. So let me bring that up. Got to go to home page 8, and that was section 2. Download that, and then I'll bring it up in Edge. I find it very helpful to use Edge. The one place Edge has actually proven to be useful is when I want to make notes on a PDF. You can use your mouse, draw very poorly like I do with like a third grader or kindergarten, but here it is. In Edge, you have the little drawing tools that show up. Text 3.2, and here we go. So this opens an Edge, and I can turn on drawing or highlighting and make notes, and it will save it as a highlighted PDF. So just like reading the textbook, marking up your book, sometimes just going through the process of marking helps it stick in your brain. So let's jump down. Question was, just a little bit of practice when we have graphs, finding the composite. So here's a great example. F of G at 0. What does this mean? Well, means we have to, what I always like to do, whenever I see this, I always like to remind myself, that means F given as input G at 0. I think, to me, this is way better notation than this. This, to me, just is kind of confusing. I wonder, what did those math nerds thinking when they did that? To me, this makes sense. I get G of 0, and then I feed it to F. So that's just me. I like this better. So let's get G of 0, and then we'll find out what number that becomes. So we come over here. We're looking for G of 0. Well, that means when I have an input of 0 here, what does my graph come out to be? Well, let's see here. Let's go down to where x is 0 right here. And I see that at x equals 0, if I zoom in there, I see that that's a -1 right there. So it hits -1. So G of 0 equals -1. Now, I know that f of G of 0 is the same now as f of -1. Okay, so that's my x and y. So I look for where is x equal to -1, right here. And the graph hits at -2 when x is -1. So I know that f of -1 equals what? -2, right. So therefore, that's equal to f of G of 0 is equal to f circle a composite G of 0. So let's do one more, just for a little practice on using graphs to find it. I immediately look at this. What I do, I'd say, well, that's the same as G of f of 2. Find f of 2, then I'll put that number there. Okay? So what is f of 2? Let's find out. F is here. F of 2, well, I find out where x is 2, right there. The graph takes me there. At f of 2, the graph is at 1. So f of 2 equals 1. Now, g of f of 2, well, that's the same as g of 1 now. So now I come over here and look for g of 1. And I find x of 1, and look at there. Lo and behold, when I have x equals 1, the graph is at is at 0. The graph is at 0 when x is 1. So g of 1 equals 0. Therefore, g of f of 2 is the same as g of 1 is the same as 0. And sometimes working from the graph, remember working from the graph, if they ask you for f of 3, well, I don't quite know. I can kind of take a guess. F of 3 isn't clear on this graph. So usually with graphs, they usually are nice to you and only tell you or give you a nice graph that crosses at specific points, easy to tell where I am at particular values. So they usually pick a function, either linear or quadratic. So, any other questions on anything? Okay, I'm ready to go to the next topic, inverse of functions. So let's take a look at that. It's like a different topic, a little brain switch. What we're thinking of is, first of all, they want to talk about functions. Remember, go way back to the beginning. Functions, whether or not they are one-to-one. When we first, yes?
I was just going to skip 3.2. Like I was just talking
What?
3.2.
Thought we did that. Did I? 3.2. That was Thursday. We did 3.2. That's in the recording. Yeah, we did 3.1, 3.2. That was the 3.2 was the composition of these different functions. I went through all of this. If you need to, let me know and I can go over some of that. But we did all this last Thursday. Right? Composite functions. Yeah. So check the video. I'll upload that. If I missed anything, I'm happy to go back over it if it was foggy or anything. Okay? So way back at the start, when we were doing our functions, just the definition of the functions, we weren't doing one-to-one. Remember, we were looking to say, does a function, the function hasn't, they're not right on the board since people are going to be seeing only the recording. When we had a function, let's see, I do have a little drawing thing going here. When we had a function, we could say, hey, is this a function? How do we know it's a function? Remember our little vertical line test. If I have an x, do I get a known y, or is it questionable? Could I have multiple choices? So we did that vertical line test. If I have a function like this, well, when I have an x at a certain value, I'm not sure which y you're talking about, because at f of 1, I get lots of possible values. So we'd say, well, this is not a function. This was way back at the beginning when we started talking about functions. Now we're looking at something a little differently. Do we have a function that is one-to-one? Well, let's think about what they're talking about. When I have a y value, I only have one input that generated that y value. So, for example, if I have a function that's a horizontal line, is that one-to-one? For every x, I get the same value. Fit one-to-one? It's a function, it passes the vertical line test, but it's not one-to-one, because I can have many x's give me the, let's say, we'll just say y equals 3. Any x gives me the result of 3. It's not 1 to 1, because 1 gives me 3, 0 gives me 3, negative 1,000 gives me 3. It is a function, but it's not 1 to 1. I don't know what x got me to 3, because any x will give me to 3, because it's a horizontal line. This function here, a nice linear function. If I were good, that'd be a straight line. If I have an x of, say, negative 1, I have a y here. Does any other x get me to that y? No. That makes it 1 to 1. And that leads us into the topic of inverse functions. If I know that there's a 1 to 1 pairing, for every x, I get a different y. That's one way to think about it. Every x, I get one y, and it's different from all other y's at that position. So they call that the horizontal line test to determine if it's 1 to 1. The vertical line test is there to tell us, is it a mathematical function at all? We don't even look at it if it doesn't pass the vertical line test. Now, if it also passes the horizontal line test, then it is 1 to 1. Some of our favorite functions, you take trigonometry, remember those fun sine functions. You've got some vibration happening in a function over time, or the wheel rotating. You get a sine function. And I know how high my spot is on the wheel if I've turned it 3 times, but it does not pass the horizontal line test. It is not 1 to 1. I have many places in time or in my x that hits that same value. It's a cool looking function. I've got waves, but it's not 1 to 1. So a lot of our trigonometric functions, sine, cosine, anything that gives me these cool waves, as cool as they look, they're not 1 to 1. So we don't have an inverse for them, except within certain regions. I can say, well, within this region here, I know what y gets me to particular values, but it keeps repeating. So, but within certain regions, I can say, yeah, it's 1 to 1 within that region. It passes the horizontal line test within a certain region. They're actually there to there, right? So I can look at functions in particular areas, but let's look at some simpler ones before we think about those fancy ones. Is this 1 to 1? We've got to look at the pairs one by one. X gives me 2, or 9 gives me 2, 3 gives me 5, 2 gives me negative 3. Oh, but 8 also gives me a 5. 3 gives me a 5 as output, and 8 gives me a 5 as output. Therefore, it is not 1 to 1. There, I have a 5 from 2 different x's. Therefore, for every x, there is not one y value. For every y value output, I have 2 different x's, so not 1 to 1. Let's take a look at this one. With the reading we have here, a 1. Well, first of all, I have, this one here. This isn't even a function, right? I get the same x, 2 different y's. That already fails that it's not a function test. So I don't even have to look at others. I don't have a unique x to a unique y. So nope, that fails. That's not even a function. Because the same x gives me 2 different y's. That goes way back to our first chapter. Functions have to give you a specific value for a specific input. How about this one? 1 to 2. First of all, I see all different x's. Now I just check for, yes, are they all different y's? Yep, that looks like a function. That is a function. Does that make sense to you? Just the 1 to 1. We're talking about this just so then we can start thinking about fancier things called an inverse function. Why does they keep coming over to this?
So it can have the same x, but it has to be the same y if it has the same x.
Yeah, if you have the same x and y, say a 1 and a 2, and then lots more things, and then you come across a 1 and a 2 again, well, it's the same pair.
So it's
You're good.
function.
It's basically listing the same point on the graph twice, usually by accident. But as long as it's unique, that every x has a specific y, every y has one x. And and not a different x? Good question. Okay, so this one, is that one-to-one? It's a function, passes the vertical line test, but nope, it doesn't pass the horizontal line test. Different x's can give me the same y, so no, that's not one-to-one. So I don't even have to look at a pair. I can just say, well, this x gives me that same value of y. This x gives me the same value of y. So nope, it's not one-to-one. Cool looking function. In this direction, it is a function. Usually this is time as things are vibrating or moving along the road when I have a wave in the road, all sorts of cool stuff. Usually, if you have a linear function, they're most of the time one-to-one. Because I have an x, and there's one place I cross on that y. I have a y, and it came from one place on the x. So usually linear functions are good. So yes, that's one-to-one. The only time a linear function is not one-to-one, or not one-to-one, is either if it's a vertical line, of course that's not a function, or if it's a horizontal line, because many x's can give me the same y. Otherwise, you see linear, if there's any tilt to it at all, one-to-one. You can check that off right away.
So you would use a vertical line test on none of these?
Yeah, the vertical line, you can always start with the vertical line to see if is it a function at all. If it's one-to-one, you got to do both the vertical line test and the horizontal line test. That's your one-to-one test. So they go through the answers. Yep, not one-to-one because I got the same y, different x's. So it is a function, but it's not one-to-one. Different x gives me the same y. But that third one, it's not even a function. It is not even a function since 3 gives me two different values. Okay, so they explain those in the textbook as well. So let's do a couple of our own just for practice. Then we'll talk about the inverse function. Let's just make up some here. You can't get too fancy, but how about this one? We've seen this one. Y equals x squared. It's a function. Is it one-to-one? Because -2 gives me 4, and 2 also gives me 4. So -2 squared and 2 squared both give me 4. It's a very common quadratic function, but not one-to-one. If I said, for all positive x's, is it one-to-one? The answer would be yes. So if I have to define the domain of anything positive, square root, then I'll say, okay, it's one-to-one for that specification. But for all x's, negative to infinity to positive infinity, it is not one-to-one. But most of the time in the real world, real problems deal with positive numbers, positive square roots. How about this one? Y equals x cubed. Do you think that's one-to-one? Well, we could do the graph. Go to my favorite place and do the graph, GeoGebra.com. Trump's making a news. Don't even have to sign in, just to play with the calculator. Let's put in the function. As the website comes up slowly. Let's put in x caret 2. Enter. There's my. Oh, now we want to change that to 3. X caret 3. X cubed. Does that look one-to-one to you? What do you think? Let's do the horizontal line test. Yep, it only hits one place horizontally. Vertical line test. So yes, x cubed is one-to-one. So back here in our little practice, x cubed, let's go ahead and graph it. We can either graph it by hand or go to GeoGebra or some other calculation. And I see, okay, horizontal line test passes, vertical line test passes. So yes, that is one-to-one. And the whole reason we're looking at one-to-one is because we're going to be working into this idea of the inverse function. We don't even think about inverse function if we don't already have a one-to-one function. So that's why they're spending time on this whole one-to-one thing. Because We want to figure out this thing called inverse, which is a very powerful mathematical concept, part of algebra. Okay, so the little explaining here of an inverse function. I have a function that has an input in a set A, remember that's my domain, to an output of set of numbers, that's my range. Why did I get domain? That's weird. I have an output to a range. Remember, the input is my domain to my function, the output is my range. Suppose I have some function called the inverse function that for any number in the range, it takes me back to the original domain. And I get back the exact same input I originally gave to this function, f. We call that function the inverse. And here's how we look at it. If I have a function g, and g, if it feeds the output of x, gives me back exactly the x that I started with here, then g is called the inverse function, and we give it that notation. F, it's not f to the -1 power, it's f inverse. And sadly, this is kind of confusing. I'd rather, when you ever see f -1, it's not the same as 1 over f of x. That is f to the -1 power. That's not the same thing. F inverse, I'd rather say f inverse. Keep that in mind. If you see f -1, that means the inverse of the given function f. Well, that all can be confusing. It's just explaining what they mean when you see this terminology here. Let's do a few practice things to see how we find this thing called an inverse function. So first thing we do is, first of all, let's just determine, first of all, is the function 1-to-1. Without being 1-to-1, I can't find an inverse. Then what we do here, and let's just do an example here. Without an example, I find it hard to understand this stuff. So I'm going to write an example right as we go. Let's give a function f of x. Let's make it a really simple function to start with. Let's have f of x equal x plus 3. We just add 3 to any number you give me. Can you tell me what the inverse of that would be to get back to my original number? If I say, give me a number, I'll add 3 to it, and I'll tell you, well, my result was 5. What number did I start with? 2. So you already did the inverse function for a very simple linear function. That, hey, if I know that my function does x plus 3, and I got 5, you automatically think, oh yeah, you started with a 2. Well, you just did automatically an inverse function in your head by saying, wait, I know that if you give me x plus 3 and I get a y, what was my inverse function? Any number I give you, you know what number I started with by just subtracting 3 from it. So here's how I found my inverse function. Already I know that if there's an x in there, it's going to be a line. There's no x squareds in there. And I could even in my mind think, well, the graph of that would look something like this. It crosses at 3 and it has a slope of 1. I can tell that a linear function is 1-to-1. If I ever start here, I know I can go and find out what you started with. But here's what they say. Interchange the x and y. Okay, let's do that. We'll say y plus 3 equals x. And now solve for x. Solve for y. New function is the inverse function. Y plus 3 equals x. Well, subtract 3 from both sides, and I see y equals x minus 3. This is my new inverse function, and now I can say, instead of y, I can say f inverse of x equals x minus 3. For this very simple example to walk through what they're saying here. to find what we call the inverse function. First of all, it's 1 to 1. Yep, it's a line. It's not horizontal. It's 1 to 1. And it's not vertical line. Interchange x and y. Solve for y. And call that f of negative 1. Well, now that we've practiced composite functions, let's see how this works. What do I get when I do f inverse of f of x? Well, f inverse of f of x is, well, f inverse takes whatever it gets for input and subtracts 3, and its input is f of x, so I say f inverse of f of x is, there's f of x, and I take 3 from it. And what do I get out? X. F inverse of the original function, if it's the correct inverse, will always give me back my x I started with. That's the whole thing about inverse. It gives you back, it takes you back to the x you started with. And in mathematical problems, that's a very important function if I can find it. I can undo what my original function did to me. And we're going to start with really simple functions and then just get a little more complicated. We're not going to give the super complicated ones. But the whole idea of this the inverse of a function, if you feed it the original function, will get you back your x. Okay, so they're doing simple, even simpler than that. If I know I have a point 1, negative 2, what's the graph of the inverse? Well, if you give me the negative 2 as my input, it would take me back to the 1. Well, I simply interchange the x and y. I only have a point as my graph. I know that negative 2 will take me back to 1 for my inverse function. That's the only, if I only know about 1 point on a function, and that could even be my only relation, I know that if I start with 1 and I get to negative 2, well, to go the other way, if you gave me negative 2 as my input, the inverse function would take me back to 1. So when you have simple point or a list of points, all you have to do for the inverse is just switch the order of x and y and all your pairs, and they'll do that for some functions. Let's say, here's the table, x and y's. What's the inverse table? Just switch x and y's around, and you've got the inverse. Now this one is basically the same kind of thing. I know that an input of 3 gives me an output of negative 1. Well, there's my xy pair. Well, then I know that if you feed me a negative 1 to the inverse function, by definition, the inverse function, if fed a negative 1 as input, it will give you back what I started with the original f. So by very definition, a function with a certain input gives me a certain output. The inverse function, if given that output, will get me back to that original input that was fed to the original function. So when you have point pairs, it's just switching around the x and y's. Now let's do a little bit of practice without, first of all, before looking at their answer, I find if you do this, and even working through this, either on paper or just on your own notes, you can first look at the solution, but come back and say, okay, can I do this? I have a 1-to-1 function. First of all, is it 1-to-1? Let's check. 8, 3, 9, 11. Unique outputs. Negative 1, 2, 5, 7. Unique inputs. Yeah, 1-to-1. Domain, that's all my inputs. Well, the domain is negative 1, 2, 5, 7. Those are my inputs. The outputs is the y's. So the outputs is 8, 3, 9, 11. And it doesn't matter if you sort them smallest to largest. The domain of f of negative 1, or the domain of f inverse, well, that's the same as the range of f. Well, here's my range of f. I'll just say, well, there's the domain of my inverse. And the range of f of the inverse gets me back to my original domain of my original function x, f. So it's the same as the input that I started with, negative 1, 2, 5, 7. Or curly brace, that should be curly brace. Okay, let's just check, did we get it right? Here's my input. It is f of inverse. The one-to-one function is simply, I didn't do this part, switching around the x and the y's for every point. I forgot to do that. That when they say find the inverse, they mean f negative 1. The relation is the points just with x, y interchanged. Forgot to do that. You curly brace around the whole thing. There's my domain of my original starting function, the range of my original starting function, and then the inverse is basically its domain is what you started with, its range, and its range is the original input to f. So, in general, what they say is the input of f, or the domain of f, becomes the output, the range of f of negative 1. Basically saying you, f of negative 1 gets you back to what originally was fed to f. F's range fed to f is what becomes the input to f of negative 1. So the output of f becomes the input to f inverse. F inverse's output takes you back to the original input. For every point, for everything that was fed to f, as defined for the function f, becomes the input to inverse, takes you back. Seems like ought to be pretty easy as we start looking at, first of all, we're not going to do graphs or algebra yet, we're just going to look at the function. What's the inverse? Well, simply switching x and y. Inverse gets the output of the original f, gets me back to negative 3. What you're seeing here is the output of f, f of x, fed back to the inverse, gets me back to my original input that I get. Well, basically what we're saying is f inverse of the original output of x, what does it give me? It's always going to give me x that I started with. Get x, get some output, feed it to the inverse, it'll get me back to the original input that was fed to f. So I see, here's my x, feed that into f of negative 1, or f inverse, I get back out of the inverse the number I started with. That's what this whole chart is telling you. If they want you to give it as a chart, real easy, just reverse x and y, or x, f inverse of that. So basically you're just switching the two rows around when you're looking for the inverse, given a table. All right, now we're going to get close to doing a little bit of algebra soon here. Let's practice just on tables here, just to make sure we get a good understanding. F of negative 2, okay, input is negative 2. What do I get? I get 6. F of negative 2 gives me 6. Find x when f of x equals 8. Basically, that's essentially doing the inverse. So all those questions asking you what x gave me certain, you were doing a little bit of inversing back then. What is x when I got an output of 8? Well, it better be 1-to-1 or I can't answer the question. I see that I get an 8 when I have an input of -4, is there any other input that gives me 8? Nope. So therefore, x had to be -4. There is no other x that gave me an output of 8. So basically, this is the question: what is f inverse of 8? That's essentially what this is asking. What x gave me 8 as its output? Well, f inverse of 8 will give me a -4. And when I fed -4 into the original function, I got out 8. All right, so f -1 of 0 means what x gave me an output of 0? Well, the only x that gave me an output of 0 is here, so I know that my x that gave me output of 0 was 8. So basically, another way to look at it is, if this becomes the input to my function, this is the output of the inverse function. Will always go exactly, take you this direction. As defined. An inverse is, that's what it does. If it doesn't do that, it's not the inverse function. It might be close to the inverse, but not the inverse. All right, so they walk through that, showing you how we got those answers. And now, I think we're going to start doing, okay, we'll do a little graphing now. Well, graph is essentially, when you have point graphs, you're essentially looking at a table just in a different way, right? You just have point pairs, and what's the question? Basically, the inverse is just reversing the x and the y. And let's just do that by hand, just so we see, we're going to start to see graphically what we're doing here. So, -1, 1 becomes 1, -1. Okay, so x of 1, y -1, about there. 3, or -3, 2. The inverse is 2, takes us back to -3. So 2 takes us back to -3 about here. And -5, 4. Well, 4 takes us to -5. In the inverse, okay, so I have x, let's see, that was a 1, 2, and a 4 is about here. Takes us way down to -5. Do you see, well, I haven't done the greatest graphing, do you see that basically, if we do it on this graph, the 1 takes us to -1 here, 2 takes us to -3 here, and a 4 takes us to -5 here. If you look carefully, you will see that the inverse is actually a reflection of the original function around this x equals y line. If I simply flip my graph around, any function I have here the inverse will always be basically a reflection of the original one around that diagonal line. A little insight into how this whole inverse function works. You kind of see that where if I'm switching x and y to find my inverse, switching x and y is the same as reflecting it around that diagonal line. So as we do lines and graphs and things, we'll start recognizing, oh yeah, that's just a reflection around that line. But we're not quite there yet. Let's see, we're going to do some algebra first, or we're going to do a couple more points. And they did it on a different graph, but there's their points. They're going to talk about the reflection. There we go. They mentioned that, yeah, look at that reflection is kind of to confirm for me, yep, I've got the right inverse function. Well, since we can do the reflection, well, here they basically would say, do that by just graphing it. Well, let's see if we can do this by hand. I've got the diagonal line. I'll kind of draw it here just to remind me where it is. If I did a reflection of that, can you see that? I'm going to do a different color here. Let's change my color. Let's change it to green. See if it shows a little better on the screen. the reflection of that would be, let's see, around that would be something like, does that show up okay up there? Sorta. We don't have really good colors on that projector. But they show the reflection of that, and then we eliminate our original. How about over here? What if we did this? No, we won't go to GeoGebra yet. We'll get some fancier functions yet. All right, now we have a few functions that we're going to practice now calculating an inverse. Now remember, we did the last one. I did f of x equals x. Let's give it a different one. Let's say x times 2. Let's say f of x equals 2x. All right, how do we get the inverse? Well, switch the x, and remember this is like the y equals 2x. Switch the x and the y, which gives us x equals 2y. Solve for y, divide both sides by 2. X over 2 equals y. Well, this becomes my inverse. Now I know f of negative 1 of x is x over 2. Well, let's do the same thing over here. H of x, remember it doesn't matter what letter I use, h of x equals 4x minus 7. Well, let's do what they show us how to find the inverse. We replace f of x with y, or in this case, h of x. So I say y equals 4x minus 7. Now, I switch x and y. X equals 4y minus 7. Now, solve for y. Well, add 7 to both sides. X plus 7 equals 4y. Get y by itself by dividing everything by 4. And I get y, or x plus 7, divided by 4 equals y. There is my inverse. Let's do, getting a little more challenging here, but let's work through the same steps on that one. I'll change the pen color for that one. Orangish. We'll start again. Y equals the cube root of x plus 1. Switch x and y. X equals cube root of y plus 1. How do I get y by itself? Well, I better cube everything. X cubed equals y plus 1. And look at that. To get y by itself, just subtract 1 from everything, and I get x cubed minus 1 equals y. Oh, and I forgot to do that last step. Equals f inverse of x. X cubed minus 1, cube root of x plus 1. Let's go to our friend GeoGebra. That's a fancy one. Let's see how that comes out. I'm going to go GeoGebra, and I'm going to put in f of x. I'm going to erase my original ones. The first one was the cube root. What was it? Cube root of x plus 1. Well, in the calculator, to do cube roots, I do x plus 1, the quantity, to the 1/3 power. That's the way I can do cube roots in GeoGebra. There is not a cube root function, but to the 1/3 power is the same as the cube root. And there's the function, cube root of x plus 1, graph for us in GeoGebra. Now let's see, they say, well, according to, if I did it right, the x cubed minus 1 should be the inverse. Well, let's see what x cubed minus 1 looks like. I'll put x caret 3 minus 1 and hit enter. Look at that. Does that look like it's a reflection of the original function around the x equals 1? Let's just graph x equals 1. X. There's my line of reflection. Does that look like it's reflected around that line? I think it does. Therefore, I can say, yep, the calculations of those two functions are reflected around the x equals y axis. Yep, they sure look like they're inverse functions. That was just using GeoGebra to kind of verify, did I get the right answer here? How about this one? Think you can do that one? If you're watching the video, I have pause it. See if you can get that. Let's do it real quick here, man. Why? Oh, I'll do a different color. Let's change it to blue. Baby blue. Erase. So, we put y where the function is. Y equals 5 over x plus 3. Switch x and y now. X equals 5 over y plus 3. Now, how do we get y by itself? It's a little tougher. Let's multiply everything. Whenever you see something at the bottom, you don't want that to be in the denominator. So multiply both sides by y plus 3. So y plus 3 times x equals 5. Now I can divide everything by x to get y plus 3 by itself. I could have done it in one step, but I'll do it in 2 steps just to make it very clear. Y plus 3 equals 5 divided by x. One caution here, whenever I do this, remember that x better not be 0 if I do this. So we might put a little note. This is all good except for when x is 0. Otherwise, it's fine math. Now what I can say is, okay, how do I solve for y by itself? Well, subtract 3 from both sides. And I get y equals 5 over x minus 3. So this is all good except for where x is 0. Things blow up. Let's go to our friend Mr. GeoGebra and see what I get. 5 over x plus 3. Over here, and I'll just hide those for now. I'll leave the reflecting line here. I go 5 divided by the quantity x plus 3. Gives me that. And notice how that function has something funny happen right here, right? When x is negative 3, it goes way positive or way negative. Well, what was our other function? 5 over x minus 3. Let's put that in here now. 5 divided by x minus 3. And look at that function. It does a very similar thing when x is 0. Strange things happen because that blows up. But it's the reflection of that original one. And I see that reflection. Yep, I must have got it right. Besides having fun playing with graphs in GeoGebra, I can kind of see, yeah, I see that's the reflection around that x equals y line. You don't have to use GeoGebra, but I find it entertaining and a little bit relaxing. Kind of visualize it and do whatever you can to relax your brain as you think about this and come across saying, okay, this is making sense to me. Another way that I relax my brain or look at it a different way would be to go on YouTube and search for inverse functions. And I found what seems to be a decent video. So let's relax our brain a little bit, because we've been taking notes, looking at this for a while. Let's see if this, generally Khan Academy stuff, gives pretty good videos. Let's see how they do it there. It's only a few minutes, kind of related, relax, and let's take a look at how.
Think about what functions really do. And then think about the idea of an inverse of a function. Let's start with a pretty straightforward function. Let's say f of x is equal to 2x plus 4. And so if I take f of 2, f of 2 is going to be equal to 2 times 2 plus 4, which is 4 plus 4, which is 8. I can take f of 3. F of 3, which is 2 times 3 plus 4, which is equal to 10. right? 6 plus 1.
So let's think
So
about
let's
it
think
in
about
a
it in a
little bit
little
more
bit
of
more of an
an
abstract sense.
So there's a
So there's
set
a
of
set
things
of
that I
things
can
that I can input into this function. You might already be familiar with that notion. It's the domain.
The
The set of
of
all the things
that
that I can input into that function. That is the domain.
That
That
is
is
the
the
domain.
domain.
And
And
in
in
that
that
domain,
domain, 2 is sitting
there,
there,
2 is
2 is
there,
there, you have
3
3
over
over
there.
there. Pretty much you can input any real number into this function. So this is going to be all reals, but we're making it a nice contained set here just to help you visualize. Now,
when you
when you
apply
apply the function, let's think about what it means to take f of 2. We're inputting a number 2,
and then the
and then the
function is
function is
outputting
outputting
the number
the number
8.
8.
It
It is
mapping
mapping
us
us from
2
2
to
to 8.
So let's
So
make
let's make
another
set
here
here
of
of
all
all
the
of the
possible
possible
values
values that my function can take on.
All
All of the possible values that my function can take on, and we can call that the range.
There
There are
more
more
formal
formal
ways
ways to talk about this, and there's a much more rigorous discussion of this later on, especially in the linear algebra playlist.
But this is
all
all
the
the
different
different
values I can take on. So if I take the number 2 from our domain, I input it into the function, we're getting mapped to the number 8. Let me draw that out. So we're going from 2 to the number 8 right there. And it's being done by the function. The function is doing that mapping. That function is mapping us from 2 to 8. This right here, that is equal to f of 2. Same idea. You start with 3. 3 is being mapped. 3 is being mapped by the function to 10. It's creating an association. The function is mapping us from 3 to 10. Now, this raises an interesting question. Is there a way to get back from 8 to the 2? Or is there a way to go back from the 10 to the 3? Or is there some other function? Is there some other function? We can call that the inverse of f that'll take us back. Is there some other function that'll take us from 10 back to 3? We'll call that the inverse of f. And we'll use that as notation. And it'll take us back from 10 to 3. Is there a way to do that? Will that same inverse of f, will it take us back from, if we apply 8 to it, will that take us back to 2? Will the inverse of f, if we apply it to 8, will it take us back to 2? Now, all of this seems very abstract and difficult. What you'll find is it's actually very easy to solve for this inverse of f. I think once we solve for it, it'll make it clear what I'm talking about. The function takes you from 2 to 8. The inverse will take us back from 8 to 2. So think about that. Let's just define, let's just say y is equal to f of x. So let's say y is equal to f of x. So y is equal to f of x is equal to 2x plus 4. So I could write y is equal to 2x plus 4. And this, once again, this is our function. If you give me an x, it'll give me a y. Well, we want to go the other way around. We want to give you a y and get an x. So all we have to do is solve 4x in terms of y. Let's do that. If we subtract 4 from both sides of this equation, let me switch colors. If we subtract 4 from both sides of this equation, we get y minus 4 is equal to 2x. And then if we divide both sides of this equation by 2, we get y over 2 minus 2, right? 4 divided by 2 is 2, is equal to x. So if we just want to write it that way, we can just swap the sides. X is equal to 1/2 y, same thing as y over 2, minus 2. So what we have here is a function of y that gives us an x, which is exactly what we want. We want a function of these values that map back to an x. So we can call this, we could say that this is equal to, I'll do the same color. This is equal to f inverse as a function of y. Or let me just write a little bit cleaner. We could say f inverse as a function of y. So we can have tan. So now the range is now the domain for f inverse. F inverse as a function of y is equal to 1/2 y minus 2. So all we did is we started with our original function, y is equal to 2x plus 4. We solved for, over here we solved for y in terms of x. Then we just do a little bit of algebra, solve for x in terms of y, and we say that is our inverse as a function of y, which is right over here. And then if we, you can say this is, you can replace the y with a, b, and x, whatever you want to do. So then we can just rename the y as x. So if you put an x into this function, you would get f inverse of x is equal to 1/2 x minus 2.
So all you do, you solve for x, and then you swap the y and the x if you want to do it that way.
That's the easiest way to think about it.
And one thing I want to point out is what happens when you graph the function and the inverse. So let me just do a little quick and dirty graph right here. And then I'll do a bunch of examples actually solving for inverse. But I really just wanted to give you the general idea. Function takes you from the domain of the range. The inverse will take you from that point back to the original value, if it exists. So if I were to graph these, so let me draw a little coordinate axis right
A
here.
slope of 2 and a crossing at 4,
Draw a
mx plus
little bit
b.
of a coordinate axis right there. This first function, 2x plus 4, its y-intercept is going to be 1, 2, 3, 4. Just like that. And then its slope will look like this. It has a slope of 2. So it will look something like its graph will look. Let me make it a little bit neater than that. It looks something like that. That's what that function looks like. What does this function look like? What does the inverse function look like as a function of x? Remember, we solved for x, and then we swap the x and the y, essentially. We can say now y is equal to f inverse of x. So we have a y-intercept of negative 2, 1, 2. And now the slope is 1/2. So the slope is 1/2. The slope looks like this. Let me see if I can draw it. The slope looks, or the line looks something like that. And what's the relationship here? These look kind of related. It looks like they're reflected about something. And it'll be a little bit more clear what they're reflected about if we draw the line y is equal to x. So the line y equals x looks like that. I'll do a little dotted line. Right? The line y equals x looks something like that. That is the line y is equal to x. And you can see you have the function and its inverse. They're reflected about the line y is equal to x. And hopefully that makes sense here, because over here on this line, let's take an easy example. Our function, when you take 0, so f of 0 is equal to 4. Our function is mapping 0 to 4, right? The inverse function takes f inverse of 4. F inverse of 4 is equal to 0, or the inverse function is mapping us from 4 to 0, which is exactly what we expected. The function takes us from the x to the y world, and then we swap it. We were swapping the x to the y with the inverse. That's why it's reflected around y equals x. So this example that I just showed right here, function takes you from 0 to 4. I should do that in the function color. So the function takes you from 0 to 4. That's the function. F of 0 is 4. You see that right there. It goes from 0 to 4. And then the inverse takes us back from 4 to 0. So F inverse takes us back from 4 to 0. You saw that right there. We evaluate 4 here. 1/2 times 4 minus 2 is 0.
So he almost showed exactly what the book shows, but what did he do different here? He solved for y, and then later on said, okay, that y is just a placeholder for what you're feeding the inverse function. We can call that x after we've solved it for y. So rather than in the book, what they say, oh, well, switch x and y and then solve for y. Well, he just says, well, solve for x, and then later on, you can say, well, x is just a placeholder for any number, make that, or y is a placeholder for any number, make that an x. So switching x and y, again, in the reflection, what do you see? If you change the pairs around, 1, 2, the point 2, 1 is the opposite side of x equals y, if you think of it that way. So the whole point is, if you need a little relaxation or a different look at it, just do a search. YouTube or Khan Academy is a great place. Just search for algebra, inverse functions. There's lots of great ways. Some will do really goofy. Some will be hardly understandable. You may come across the one that says, oh, that really clicked when I saw that video explaining it. Make a note of what that link was or who that was and how they explained it. You might find, that when I go to that, I understand it better. Use that for study aids, and if you can find a good link, I'm happy if you send it to me. I'll put it in, hey, here's some good videos help you understand this. Because the whole point is we want you to understand this, to pass the course, get a good grade. And all our brains don't understand things the same way. You feed it a certain way in the concept. For some of us, it clicks right away. For others, they look at it this way. Oh, yeah, that makes more sense. So I'd love to help make it sense to you. That's my whole purpose in life, is help make all this stuff make sense to you. Okay, so close that video down. Khan Academy videos, generally pretty good. Sometimes they're really confusing, but usually pretty good. Okay, so back to our textbook. We went through the different functions, x plus 7 divided by 4. There's their answer. Yeah, we got it right. Cube root looks kind of scary, but if we just solve for, switch x and y and then solve for x, we get a decent looking function and see that we find the inverse. And there's their inverse finally they get. And it doesn't matter what letter you have, G inverse, F inverse, just like with the placeholder x is just saying, hey, some number goes here. Same with the letter for the function. Some function, I give it a name, does something to what its input is. All right. Now we're back to the graphing part, or the table part. What's missing here? Assume the function is 1 to 1. If f of 7 equals 8, find f inverse of 8. Yeah. I can just say, okay, feeding this for my x, for my f inverse, my output, if it's the correct inverse, is going to get me back to the original. So f inverse is basically, this is my input, this is my output. So yeah, f inverse of 8. Here's my input to f inverse. It gets me back to 7. So I know that if I know what number I got to get me to 8, f inverse better get me back to 7. I don't even have to look at the table to see that. If I see this, f takes me from 7 to 8, just like that mapping they showed you in that little example. If f takes me from 7 maps to 8, the f inverse better take me back to 7, or it's not the inverse. That mapping, maybe that mapping diagram will click. What happened to my mouse? Now, just a little practice with the tables. F of 5, there it is right there, takes me to 2. F inverse of 5. Now, don't go to here. F inverse of 5 means I started with an output of 5. What x got me there? Remember, I got to go to this. Don't say, oh, f of 5. That's not that guy. This is f takes 5, gives me an output of 2. F inverse, I got a 5, and I got to get back the other direction. So f inverse is 3. So even though they look similar, f of 5 don't come up to this 5. F inverse of 5 means, oh, I'm going from this as my input to get the other way. So that's my input. F of x equals 8. What is x? That's just basically asking you, what x got me to 8? Or what is f inverse of 8? Well, I got an 8 from giving it an input of 7. Therefore, answer is 7. Now, this one's a little bit confusing.
Quick question. Why wouldn't it be 4?
This guy here?
Yeah.
Well, let's take a look here. I got an output of 8. And they're asking me, what x got me there?
Okay.
So I have to get an output. Here's my output of f of x. There's my output of 8. And that's why the input 7 is what got me to the 8. Yeah. This is the x that gets me to 4. X gets me to 4 in my original lab. Okay. This guy here. F of x got me to 8. Or actually, f inverse gets me to 8. Well, what is x?
Yeah, 4. Right.
This one would be the 4. Very good. F inverse gets me back to 8. I have to feed inverse. Now, the confusing part of this is putting an x there kind of confuses you. I'd rather say, what input z gives me of the inverse takes me back to the 8. And an input of 4 into my inverse function gets me back to 8. So the answer here is 4. Now it gets a little more challenging. First thing I look at here, before even thinking about is there an inverse, it's a linear function, a slope of 10, mx plus b, remember all that? Slope of 10, crossing point at 13, and there's no exponents in there. I know it's a 1-to-1. It's not horizontal. So what do I do to get the inverse? Y equals 10x plus 13. Switch x and y. X equals 10y plus 13. Now, get y by itself. I'll come over here and subtract 13 from both sides. X minus 13 equals 10y. And now divide by 10. X minus 13 over 10 equals y. If you want to put it in mx plus b format, you could say y equals 1/10 x minus 13/10. Seeing I have a 1/10 slope, I'll minus a little bit more than 1 in the y-intercept. But I'm happy with this answer. This looks nice and neat. Y equals x minus 13 over 10. And do they give us their answer? Well, let's do it ourselves, and then we'll do it ourselves, and then we'll be done. But I don't think they give us the solutions to it, so we're doing a little practice. All right, next one. Change my color, even though on your screen it hardly changes in color. Let's do y equals 1 over x plus 5. Switch x and y. X equals 1 over y plus 5. What do I do to solve? I'm going to remember that I can multiply by y plus 5 and divide by x at the same time. I'm going to do that in one quick step. I know that y plus 5 equals 1 over x. I could remember my cross product equation, that x over 1, that is equal to that. So I can switch these two. Anyway, I get this. And then to solve for y, y equals 1 over x minus 5. There is my F inverse. I forgot to look at the 1-to-1 thing. What's one thing I need to keep in mind here? X can't be equal to -5. Things blow up, get very huge, positive or negative, at the point x equals 5. They're not making you worry about that. We just say, okay, we'll keep that in mind later on. Here, when x is 0, it's going to go way off in huge numbers. But otherwise, it'll be something calculatable. And for our last one, throwing a little bit of cubes in there. Cubes are odd powers are usually 1-to-1. Even powers give us the graphs like that or like that, and they fail the horizontal line test. When there's a cube in there, they usually look something like this, or not that bad. They usually look something like a little curvy to it. If the curve doesn't come back down and fail the horizontal line test, then we know it's reflecting. But let's take a look at this one. Let's put it in the form y equals 12 plus cube root of x. Switch x and y. X equals 12 plus cube root of y. First of all, subtract 12 from both sides. X minus 12 equals cube root of y. And what do? Cube everything. X minus 12. Make sure, 13. X minus 12. Make sure you cube the entire thing. Don't do x cubed minus 12 cubed. It's x minus 12. The quantity cubed equals y. That is the proper inverse. X minus 12, the quantity cubed equals y is our inverse function. And for our last thing, let's just graph that. x12 plus cube root of x. We'll hide the other ones. We'll leave the reflecting one there. We'll do 12 plus x to the 1/3 power. Gives us that cool looking thing. And what was the other one? The other one was x minus 12 to the cube to the 3rd power. So let's do that one. Quantity, x minus 12 to the 3rd power, enter. And look at that. They reflect nicely around the x equals y. GeoGebra just helps us confirm, yep, that's a cool reflection. Cool looking function. Scary looking at first, but if you just follow through the steps, it's not so bad. Walk through those steps they give you. All right, this will be saved to a recording, uploaded for your review. If you have a little insomnia, help you sleep.